Now there's a robot who's got heart. And that's just what we've been after. A robot heart with the power to leap to our every command. With all this energy, naturally, the battery we're using is our own high-powered design. Well, not quite. In fact, we're using commercial batteries, which don't look at all like electrochemical cells we've been building. The problem is that our laboratory models aren't much use for commercial applications. They're too large and bulky for our robots, and they spill easily. But they are useful for establishing basic principles. They've helped chemists develop half-cell tables. When two half-cells are selected, they can be quickly arranged as a reduction reaction and an oxidation reaction. Their half-cell potentials add together to give us a prediction of the battery strength. Although our laboratory models look completely different from commercial cells, they both work on the same chemical principles. In 1786, Luigi Galvani accidentally discovered these chemical principles. During an experiment, he hung a freshly dissected frog's leg from a copper hook. Galvani noticed that it twitched whenever it touched a different metal, such as iron. He found that when the leg was in contact with copper, nothing happened. Another scientist, Alessandro Volta, applying this idea of different metals, invented a primitive pile, or battery. Volta's pile consisted of silver and zinc discs, separated by cardboard soaked in salt water. Like other early cells, this primitive pile could not deliver a flow of charge over an extended period of time. A French scientist, Georges Leclanché, is credited with inventing the cell which is still widely used today. The Leclanché cell has the same important parts as our laboratory model. The anode of the laboratory model is made of zinc and is actually the container in which the chemicals are placed. The wire connected to the cathode is replaced by a carbon rod. So, where's the cathode? It's a paste, a mix of manganese 4 oxide and carbon powder located in the space around the carbon rod. The rest of the space in the container is filled with a black paste containing ammonium chloride, but we'll show it in another color to distinguish it from the black cathode. We know that in our laboratory model, a salt bridge is required. It allows ions to migrate from one half cell to the other, and at the same time, the bridge keeps the two solutions from coming into physical contact. In the Leclanché cell, a paper liner soaked in a conductive material is used to separate the anode from the cathode. The paste inside the cell is moist enough for the movement of ions. The soaked paper liner allows ions to move through it, but it keeps the anode from making direct contact with the electrolyte that surrounds the cathode. Because the cell is full of paste, our robot will be able to assume a variety of useful positions without spilling his heart to anyone. Exactly how does the Leclanché cell produce the flow of charge that makes it so useful? It's not as simple as in our laboratory model, where the reactions are well known. In fact, in some commercial cells, chemists aren't sure what the reactions are. For the Leclanché cell, they're thought to be as follows. Remember, the anode is made up of zinc atoms. They react with some of the ammonia molecules dissolved in the electrolyte. The zinc atom becomes reduced by losing 2 electrons. The resulting zinc ion combines with 4 ammonia molecules to form a zinc-ammonia complex ion. To prevent a buildup of positive charge, negatively charged chloride ions migrate towards the anode, passing through the paper liner as they do so. At the cathode, it is the manganese 4 oxide that reacts. Some ammonium ions are also involved. 2 molecules of manganese 4 oxide, 2 ammonium ions, and 2 electrons react to form manganese 3 oxide, ammonia, and water. In this reaction, positive ions are being removed. As a result, ammonium ions migrate through the paper liner and towards the cathode. So, whenever the cell is used, there is chemical activity near the cathode and around the anode, as well as the movement of ions. The amount of current a battery can deliver is obviously limited by the amount of anode that can be changed from atom to ion and take part in a reaction. Wouldn't it be nice if the anode could somehow be rebuilt and reused? Well, technology has produced the rechargeable battery. One such cell is the nickel-cadmium cell. It has a cadmium anode and a cathode in which some nickel-3 hydroxide is embedded. The 2 electrodes are surrounded by a potassium hydroxide electrolyte. To supply electrical energy, the cadmium reaction loses electrons. The cadmium is eaten away, while the nickel reaction gains electrons. When this cell runs down, it can be connected to a battery charger and recharged. The battery charger forces the electrons to flow through the circuit in the other direction. The cadmium reaction gains electrons, rebuilding the cadmium anode. But unfortunately, rechargeable batteries are expensive. Unless a battery is rechargeable, the anode continuously erodes until it's possible that the container can be perforated, allowing the corrosive contents to leak out. So, absorbent cardboard is often placed around the zinc, and the entire battery enclosed in a steel jacket. No matter which variety of battery you might use, the cardboard and steel may not hold back the contents forever. Remember, if your robot runs down, he needs a change of heart, or he may turn into a nasty drip.